Hi everyone. In this video, I'm going to go through a simple R package that I created. I'm going to explain how it works and the motivation behind creating it, and then I'm going to kind of talk you through more general principles about how to create a library. This library, or this package, is called armaOptions, and it's published on CRAN, and it's also available on my GitHub, linked in the description. For a brief understanding of how this works, it's based on one main fundamental assumption, which is that price data follows the model spelled out here, which has two components. It has the linear regression component, and it has an ARMA component. So an ARMA model is defined by this equation here. You don't need to know exactly how this equation works. Basically, what it means is that values that are close to each other tend to be very correlated. So the value with t equals 100, so x at t equals 100, is very similar to the value when at x when t equals 101, which is very similar to the value when t equals 99. And so it adds correlation to the price data values. And what we do is we take this assumption and we basically say, okay, how do we fairly price European options based on this assumption? So let's say our friend Bob wants to sell us a European option at a strike price S that expires H days into the future. We want to basically find out what is a fair price for this option. So when we look at a put option where Bob has agreed to buy a stock or asset from us, this is only valuable when the price of the asset is less than what Bob has agreed to pay, because if the price of the asset is greater than what Bob has agreed to pay, then we wouldn't sell it to Bob because there's no actual benefit to doing so, because we'd be selling it below its actual value. So I've basically written an equation here for the expected value of a option, and it basically works like this. So this is basically the value of the option given the price of the asset and the strike price. And this is the density function or probability density function of the asset. And we basically integrate over all possible values of the price at a time t plus h. And this basically simplifies into this neat little equation here, which is basically saying that the value of this option is the probability that our price at a time t plus h is less than strike price s. So it's the probability that it's profitable times the expected value of the option given that it's profitable. So it's s minus the expected value of our price at time t plus h given that our price is less than a value s. And the main goal of our package is to calculate this value here. So we'll notice, pulling back to the model we use for price data, is that all of these values here, the beta of 0, beta of 1, t and h, are all deterministic. We know what they are. They don't have a probability density function. The only thing that does is our ARMA component, x of t plus h. So what we can do is we can simplify this equation by basically substituting in the value that x t plus h has to be times the probability that x of t plus h is below our strike price or its threshold. Then this makes it much easier to calculate. And so two key steps are we estimate our residuals of our time series here. We fit them to an ARMA model. Then we forecast h days into the future. And we get this distribution function here. And then we use that and what we've calculated for s subscript r to basically solve this equation or find an accurate estimate of this equation. I'm not going to go into detail about how the forecasting works or the time series parameter works. For that, I would recommend chapters 3 and 4 of the book Time Series Analysis by Lewis Hamilton, or a package that was heavily used in my package is the forecast R package. And if you read the source code, it's very helpful to understand how forecasting is done in code and how model fitting is done as well. The logic for call options is the exact same, except in the other direction. So here I've written up a simple explanation or example of how this would work in code. So we first import the packages used. We create a simple function to estimate the conditional expectation of a normal distribution. Then we simulate our data. So this is what the data that can be used in this function would look like, or just one example. Then what we do is we say, okay, we know that this contains a linear component and a time series component. So the first thing we do is we fit our linear regression, and then we take the residuals from this linear regression and say, okay, these definitely follow a ARMA model. And so we fit this ARMA model to find our model parameters. And then we forecast into the future. So it would look something like this. This would be our forecast, and then the blue line shaded is the 95% confidence interval in this plot right here. And then, okay, great. We've fit our model. We've forecasted into the future. Now it's quite easy to calculate the value of our option. So in this example, a sell value, what our friend Bob is willing to pay for this option is €8 or dollars. And they're saying that this option expires 5 days from now. So what we do is we find our profit threshold. This is S subscript R in the write-up. And our profit threshold is this, which basically means that our value of x of t plus h, has to be less than this value, or our option isn't profitable. So what we do here is we find the expected value and standard deviation of our residual. And then we find the probability that our value of x is less than our threshold. And we find that it's roughly 60% chance. So there's a 60% chance that this option is profitable. And this value here calculates the conditional value, the expected value of x of t, given that it is less than our threshold. So we get the expected profit when profitable, which is basically saying that on average, when we win, when the option is profitable, then we win 96 cents, or yeah, 96 cents on average. And so we take that and we multiply it by our 60% chance of profiting, and we guess that this stock option, this put option would be worth 56 cents. And so this is an example. This is basically doing the same thing. So what one of the functions does in my package is that it gets the same value, the stock option value. It gets the probability of profit. It returns the expected value when profitable, and then it also returns our model coefficients. So that's how the function works. That's basically what it does. And then I expand it to use call options. And I've expanded it to loop over multiple time periods and to loop over multiple strike prices. So it's quite a simple function, quite bare bones. Like this is one of them. And then once you've written your package, once I've written my package, you have to think, okay, how will this be useful to other people, or how will I make it? And so the first thing to do is simply just write clean code, which is easier said than done. And the second thing is to write a description. Okay, what does this package do? Provides a way of to estimate the value of European stock options. And then the thing that I like the most is you create documentation. So I use Roxygen to create this documentation. And so you write it here, your parameters, an explanation of the function, and what it returns, obviously, and a simple example. And what you can do after you've created this is someone else can say, okay, what does this function even do? You can go question mark European put option value, the name of the function, and what you get is you get a description of the function, you get a usage, it explains the arguments and what it returns, and then it creates a simple example. So this means that if someone who's not the author or someone intimate with the package can easily understand how it works and what it does. So thank you for watching. This is an explanation of my R package.